So today we're going to look at the alcohols. And the alcohols are another example of a homologous series. We've seen several of these already. And the functional group is oxygen, hydrogen, sometimes called a hydroxyl functional group. And when it's by itself, so if it's OH minus, then this is called hydroxide. So for example, you will have seen sodium hydroxide, which is an inorganic compound, hydroxide, sodium hydroxide. And as with all the other homologous series we've seen, we can name these very straightforwardly. So the first alcohol has got one carbon atom and it's got 4 bonds to that carbon atom, and one of them is replaced the hydrogen with this functional group here, the hydroxyl functional group, to make it an alcohol, and this is of course called methanol. So meth from the 1 carbon and anol is from the fact that it's an alcohol. And we could continue, so this is ethanol, so I'm now drawing in skeletal structure. Sorry, this is ethanol. I could continue, so this is propanol, this is propan 1ol, because it's at the end of the chain, and I could have, of course, propan 2ol, which is also sometimes referred to as isopropanol. You might sometimes call this called IPA, it's a very common solvent, and so on and so forth. So I could have this, which is pentanol, pentan 1ol, if we're giving it its full name, and so on and so forth. So these are alcohols. And we're going to look at a few different parts of their production, how they are oxidized, so some of the reactions that you can do with them, and some elimination reactions to give you alkenes. So let's start off by looking at alcohol production. And alcohols can be produced a few different ways. We're going to look at 2 of them here. The first one is by fermentation. So you've possibly heard of this before. This is how alcoholic drinks are made. So for example, beer or wine, they're both examples of making alcohol by fermentation. And here we are doing fermentation of sugars, which is commercially, when we are making alcohols, we start from glucose. And you take your glucose and you add yeast, and this is important, you then keep that mixture at a fixed temperature. So it's 15 to 25 degrees Celsius, and you exclude oxygen, and we call this anaerobic. And these conditions are important. You need to remember these for your exams. So we take glucose, we add yeast, we treat it at 15 to 25 degrees Celsius, we exclude oxygen, and this converts the glucose into ethanol. So I'll just show you the molecular formulas of each of these. So glucose is, you may have already seen, the C6H12O6, and, sorry, I beg your pardon, that should be subscript O6, and ethanol is of course C2H6O. And so this process will only ever make ethanol at maximum 15%, maximum, because, and this again is important, above 15% the yeast starts to die off. So above 15% yeast dies. So yeast is a living organism, and yeast can't survive above 15% ethanol in water. So you've got your 15% ethanol solution, and it's got a whole host of other things in there. So if you want to purify that further, you use something we've looked at before, which is fractional distillation. And that allows you to separate out everything that has a higher and a lower boiling point of ethanol from the ethanol simultaneously, and gets you up to a very high concentration of ethanol, which would be kind of somewhere in the region of 96%. ethanol. So this is one route to almost pure ethanol through fermentation and fractional distillation. Now this material, 96% ethanol, looks like this. Won't join all the hydrogens. And this material can be burnt. So this can be burnt in oxygen. And if we do that, it gives us carbon dioxide and water. Now, what else when we burn it in oxygen gives us carbon dioxide and water? Well, fossil fuels. So what we can see then is that ethanol is a fuel. It's a liquid fuel. So we can use ethanol to do things like run a car. And if we do that, it's called a biofuel. And it's called a biofuel because of where it's come from. So if we trace this back, we can remember that this ethanol originally came from glucose. And if we go even further back, we can say that that glucose could have come from, for example, mannose, which is another complex sugar, or fructose, which is the sugar from fruits, or sucrose, which you get if you grow sugarcane or sugar beet. So in Brazil, especially, large amounts of sugarcane are grown, and it's then converted into glucose and onto ethanol, and then that ethanol is used as a biofuel. And you might be thinking this is excellent and a fantastic idea because the carbon for this has come originally from carbon dioxide in the atmosphere, because these are plants. So these plants take in carbon dioxide and water, and they convert that into the sugars in the plants, and that gets then converted into ethanol, which is then burnt and releases the carbon dioxide in the atmosphere, and we have a carbon cycle. So on the face of it, this looks like a really good way of making a fuel. It's much better than fossil fuels because we aren't taking the carbon out of the ground where it's kept in a very long-term storage. And so this could be considered to be a carbon neutral fuel. However, real life, as ever, is not quite as straightforward as that, and there are a number of issues with this. So there are a number of issues that you need to be aware of. So issues of biofuels. So to say this is a carbon cycle. So this carbon dioxide, if I use red, so this carbon dioxide and water can be thought of as the same as this carbon dioxide and water, and from there you follow the arrows. So you can see here that this is going all the way around here, and you can see there I've created a cycle on the red lines of the carbon. So the issues with biofuels, one issue is where the land is being used to grow the sugarcane, so land use. So that could cause ecological damage. So for example, if there's some species that only exist in that part of the world and they only exist in the environment that's naturally there, and we remove that environment like a rainforest and instead plant lots and lots of sugarcane, and those animals can't survive in sugarcane, then that's going to do some ecological damage to that ecosystem. You could get water, what's called water runoff. And this is where, again, if you remove forest, then the forest no longer provides the protection that it did before for the water. So when it rains, that water now just immediately runs off into the nearest watercourse, and it doesn't enter the ground, it doesn't regenerate the ground. You also have some ethical issues around labour. So who's doing the labour for this? Often in lower income countries, there's significant amounts of what we'd consider to be illegal labour or slave labour, and that's often not well regulated. Not just Brazil, or not in Brazil necessarily, but in other countries as well. And so there's a whole host of issues around using biofuels. And then the second issue here, the second major issue here, or this actually should be the second one. So the third issue then is the fact that when you use a biofuel, you never use it by itself. So typically biofuels are mixed with fossil fuels. Another issue is that the food production on the land is impacted. So we can't use the land that's being used to grow that sugarcane for food growth anymore. So a whole host of issues with biofuels. So on the face of it, they might seem like a really good solution to fossil fuel energy crisis. There are actually a whole host of problems with them. So let's look now at the second method of production. So this is the hydration of alkenes. So you remember we looked at alkenes recently, and that is our homologous series which has a double carbon bond in it. And so, for example, here is, this is drawing out, this is but-2-ene. Remember that we count from the first carbon in the chain that we encounter the double bond on, so 1, 2, so this is the first carbon that has the double bond on it, and so therefore it's but-2-ene. So but-2-ene, for example, we could react with sulfuric acid, or sorry, an acid catalyst. So we say acid cat and water, or steam and heat, and this would give you this, which is butan-2-ol. And this is a fairly straightforward reaction. You don't need to remember too much about it, just that you need an acid catalyst for this to progress, and it needs to obviously have water present. And I'll show you the mechanism for this, although it's unlikely that you'll be asked to produce it, but let's have a go anyway. So here is my but-2-ene. And I'm just going to represent my acid catalyst like this, H+. Now, H+, which is hydrogen with its electron removed, never exists freely like this. It's always bound to something. So, for example, in this situation, you might have water with an additional hydrogen ion like this, which is called the hydroxonium ion. But for now, for simplicity, let's just call it H+. And we'll start from our double bond, and that double bond will come and it'll pick up the hydrogen, and that'll leave us with a charged species like this, where the charge is here, and then because we're in water, I've got perhaps OH2, and that can then go along with its lone pair, and it can just attack that really positive site now. So the water isn't a particularly good nucleophile, but this positive carbon is an extremely good electrophile. So I'll just actually put here that this is a nucleophile and this carbon is an electrophile, E+ nucleophile. Although it's not a charged nucleophile, it's still a nucleophile because of this lone pair that it has on it here. So that's an area of high electron density, and it's attacking this area of high electron loss, high electron absence, if you like. So that leaves us with this, and that water can then lose that hydrogen just to another water molecule. And I'm going to repeat all of this with a skeletal formula if you prefer to see it like that as well. So I've now got OH2, this has got the positive charge in it now, and one of these water molecules, it can disappear and can be taken off by, for example, another water molecule could come along and liberate that hydrogen so that you no longer have this positive charge. And that would leave you with the butan-2-ol. Now, I'll do the same thing with a slightly different molecule. So let's use this, which is cyclohexene, and I'm going to react that with my acid cat, obviously not an actual acid cat, heat and water, and again I'll use the same notation, so I'll just use H+, and then my double bond again can come and attack my hydrogen, and then I've got this species which has got the positive charge and the H+ here, the H here, and then again I've got my water with its nice lone pair, and that lone pair can very happily come and attack this electrophile, and that leaves me with this, Now, I probably wouldn't actually draw it like that. I'd probably draw it like this instead, but I wanted to draw you this so I didn't confuse you too much. So I've just rotated the molecule by one atom around, but it's the same molecule. Obviously, I can just pick it up and I can turn it around. And so the hydrogen, which was here, is now here, but I don't draw it because I'm drawing skeletal structures, and I only drew it earlier to show you what was going on. So I've now got this molecule, which is cyclohexanol. So again, very similar mechanism, and I beg your pardon, this actually is OH2 plus, and again we just lose that that hydrogen and we get that full cyclohexanol molecule. So for example, we might have another water molecule here, and again lone pair nucleophile, and it likes this very strong electrophile, so it just picks up the hydrogen that's on here, for example, and just dumps the electrons back into the pair. I might just draw that out actually, just so you understand what's going on there. So if I've got to this point and I've got my O and I've got H, now this is an oxygen with 3 bonds, that's why it's got the positive charge. If you remember, I said that oxygen prefers to have 2 bonds, so it can in this case have 3, but to have 3 it has to be positively charged. And then if I've got my water molecule over here, and I'll just draw it out in full, and it's got its lone pair, that lone pair can very happily come and take one of these hydrogens, and when it does that, the electrons from this bond here go back onto the oxygen, and that satisfies the positive charge to become neutral. And so I'm then left with, I'll draw everything out here, then left with OH neutral, because the electrons from the bond to the hydrogen have gone onto the oxygen to make it now neutral. And I've now got this OH3, H3O plus. So I've got H3O plus, and I've got cyclohexanol. So those are the 2 ways of generating alcohols that you need to know about. So let me just summarize this. So making alcohols. 1, fermentation of glucose, and then I'll put a square bracket, add fractional distillation, let's call it frac dist. 2, hydration, we call it hydration because we're adding water across the bond, hydration of alkenes. Okay, so in the next part, let's have a look at the oxidation of alcohols. And here we go. So alcohols can be classified in one of 3 ways. And it's important that you understand this before we start talking about oxidation. So you may think, where are we going? Don't panic, this will all make sense. So alcohols can be one of 3 different types. So if I start off by just showing you this alcohol, this is propanol, and importantly it's propan 1-ol. And if I tell you that this is a primary alcohol, so just for now don't worry too much about that, just remember this is a primary alcohol, and sometimes we denote that by putting a 1 and then a little circle, so let's put that in brackets for now. If I then use another propanol, but I use propan 2-ol, so this is now propan 2-ol, this is what we would call a secondary alcohol. And see if you can spot why that might be. And again, this has got a 2 with a little circle. And then if I have another alcohol here, and I have this, which we would probably call this tert-butanol, or we could call it 2-methyl propan 2-ol, is the UPAC name. Propan 2-ol, and this one is a tertiary, meaning 3 alcohol, and we use 3 in a little circle. So hopefully you can spot why we call these primary, secondary and tertiary alcohols, and it's all to do with the number of carbon atoms that are bonded to this carbon. This is the important carbon. So the carbon that's immediately bonded to the oxygen, that's the important carbon, and then we want to know how many carbons are bonded to it. So for a primary alcohol, I've got 1 carbon bonded to it. For a secondary alcohol, I've got 2 carbons bonded to it, and for a tertiary alcohol, I have 1, 2, 3 carbons bonded to it. So again, propan-1-ol, there is one carbon bonded to the carbon which is immediately adjacent to the oxygen. In propan-2-ol, there are two carbons that are bonded to the carbon immediately adjacent to the oxygen of the alcohol. And in 2-methyl-propan-2-ol, I have three carbons that are bonded to the carbon which is bonded to the oxygen. So that possibly sounds a little bit confusing, but hopefully you can see just by looking at those drawings, those chemical structures, what we mean by primary alcohol, secondary alcohol, and tertiary alcohol. The other important thing to notice is how many hydrogens I therefore have on that carbon. So this top one, I'll draw this in red, I have 2 hydrogens. On this propan-2-ol, I only have 1 hydrogen, and on this molecule, I have no hydrogens on the carbon that I circled in red just now. So as the number of carbon atoms bonded goes up, the number of hydrogen atoms bonded goes down. And these hydrogen atoms are required for oxidation. And so the result of all of this is that tertiary alcohols cannot be oxidized. Tertiary alcohols cannot be oxidized. Primary alcohols can be oxidized. Can be oxidized to aldehydes, we'll come back to this, don't worry, aldehydes and carboxylic acids. So these are 2 new functional groups that we've just discovered. So aldehydes and carboxylic acids, and secondary alcohols can be oxidized to something called a ketone. And so we're going to look at all of those in some detail, but just to give you an idea, I'm just going to draw these out now. So this is an aldehyde, carbon double bonded to oxygen with a hydrogen. This is carboxylic acid, carbon double bonded to an oxygen, and then another hydroxyl group. And a ketone is like that. So there's a carbon on either side of the central carbon. So let's have a look at each of these in turn. So let's start with primary alcohols. Primary alcohols. So let's use propanol again. Propan-1-ol. Propan-1-ol. And we're going to oxidize it. And for you guys, it's sufficient just to write O in square brackets. And this means oxidizer. Now, you also need to know that you can use something called potassium dichromate. So I'll just give you the symbol for this now. This is potassium. So the potassium is the piece in green, obviously. Potassium, and then dichromate is the other part. So let's give that a different color. Let's make that orange. So dichromate is this part. But you would just draw it all as one molecule, obviously. So K2Cr2O7 potassium dichromate, and that's a common oxidizing agent. So if we treat this propan-1-ol with potassium dichromate, and you guys can just write your O in a square bracket above it, the first product you would get will be this. Now I'll just draw that underneath in structural formula. So I've got my 3 carbons there, and I've got a double bond, and then I've got my hydrogen here. Remember, in the skeletal formula, we don't draw all the hydrogens. So there's a hydrogen not drawn, and I'll draw it in orange now. There's a hydrogen not drawn here, and we tend not to draw that unless it's involved in a mechanism somewhere. So I'll leave it there for now. So these are the same molecule I've drawn here. These 2 are the same molecule. And this is called prop, and be careful here, anal. Not propanol, that would be the alcohol. This is propanal. And you don't need a number because aldehydes always exist at the end of the chain. So, if you leave this in the pot with the oxidizing agent and you heat it up and you aren't careful with your conditions, it will oxidize again. And that will mean it will remove the orange hydrogen that we highlighted earlier, this guy, in green. So, if it does that, then it goes up another oxidation level, we say, and it picks up another oxygen, and we now have a carboxylic acid. So this is now called propanoic acid. So remember, all you need to remember for names are the endings. So you just need to remember the endings, and everything else is just the length of the carbon chain. So I've still got a carbon chain of 1, 2, 3 carbon atoms, but in this case, I've got a carboxylic acid on the end, so now it's called propanoic acid. And this is as far as we can oxidize this. So the full oxidation of propanol, 1-propan-1-ol, with potassium dichromate will give you propanoic acid. If you are careful, if you put in just a little bit of the oxidizing agent and you don't heat it up too much, then you can achieve this propanal, which is an intermediate oxidizing product. So let's look at secondary alcohols. Secondary alcohols. And let's look at one we used before. So let's use this, which is propan-2-ol. Let's do the same thing. Let's use oxidizing agent and some heat. And this time we make this, which is called propan-2-one or propanone. This is also very commonly called acetone. This is a very, very common solvent. You might have seen this in things like nail varnish remover. So you can find this in nail varnish. Some nail varnish removers, not all. Some of them are alcohol based instead. Nail varnish remover. This is a very powerful solvent, very frequently used in chemistry. So it often gets its common name acetone, but the full name is propan-2-one. And if I leave this in the pot and I leave my oxidizing agent in and I put loads of oxidizing agent in and I really, really heat it, nothing happens. And that's because there are no hydrogens where I've just drawn one. So there's all of my bonds to this carbon in blue, in turquoise. They've all been used up. I've got 4 bonds to that carbon. And you need that hydrogen there to have an additional oxidation step. So secondary alcohols, dead easy, because you can only get one product from them and it's always the ketone. This is a ketone. So we've had a ketone, we've had up here an aldehyde, and we've had a carboxylic acid. And these are the 3 possible oxidation products of alcohols. But you can tell almost all the time what you're going to get, because if you've got a secondary alcohol, you're going to get a ketone. And if you've got a primary alcohol, you're either getting an aldehyde or a carboxylic acid, and it will depend entirely on the conditions that you use and to how hard you hit it, how aggressive you are with your reaction conditions as to whether or not you got your aldehyde or your carboxylic acid out. So if you've got a question about this, and they're being very, very careful to tell you what the reaction conditions are, it's probably because you're expected to work out whether you're going to get the aldehyde or the carboxylic acid out. So secondary alcohols, as we've said, have a ketone product and that's it. And tertiary alcohols, and I'll just put this down for completeness, tertiary alcohols, so for example, if I had this one and I hit it with lots of heat, lots of oxidizing agent, I would just get exactly the same thing back out. So that's oxidation, and you need to be able to write equations for those oxidation reactions using this O symbol like here, and you need to understand that there are different methods used in the oxidation of primary alcohols and to get 2 different products, aldehydes and carboxylic acids. And then the final thing we need to talk about are chemical tests. So chemical tests for ketones, aldehydes, and there are 2 you need to know. One is called Fehling's reagent. Sometimes very similar to Benedict's. Similar to Benedict's. Or you can have Tollen's reagent. And Fehling and Tollens are just people's names, just they came up with these reagents, so they've had them named after them. Isn't that nice? So if you imagine that if I've got an aldehyde, this can be oxidized, as we know, to the equivalent carboxylic acid. So if the aldehyde can be oxidized, what's happening to the electrons? Well, if you remember the nice little acronym oil rig. So this is oxidation is loss. Oxidation is loss, and then I always put at the end in brackets of electrons. And then the other side is rig, which is RIG, and that is very simply reduction. So if you reduce something is a gain, and then again I put in brackets of electrons. So if I've oxidized my aldehyde to my carboxylic acid over here, that means oxidation is lost. That means there has been a loss of electrons. And that must mean, therefore, that must mean another species somewhere has been reduced. And that is the Fehling's reagent and the Tollens reagent. They are what get reduced. So in the case of Fehling's, let's treat that one first. Fehling's reagent is a copper 2. And if you remember some of your colour chemistry, this is a nice blue colour. It's a nice blue solution. And if I reduce copper 2, it goes to copper 1. And that is a red precipitate. So if you add your copper solution and your aldehyde, so if I add my aldehyde is oxidized, so I end up with a carboxylic acid on this side, carboxylic acid. So that is oxidized, so let's use yellow for oxidized, so this is oxidized, and the copper has been reduced, so reduced. Now, the way you can get your copper into solution, there's lots of ways of doing it. Fehling's uses a specific way, and so they might give you some more detail, but the important thing is that there is copper 2+ in solution, and you end up with copper 1+. So this could be called copper 2+, and this can be called copper 1+, or just copper plus. And this has gone down an oxidation level. So copper 2+ to copper 1+, that means that it has, if you remember, it's been reduced, so that means it's gained electrons. So this means it's gained electrons plus E-. And down here we've oxidized something, so this is lost electrons. For the Tollens reagent, it's very similar, but instead of copper, we have silver. So you might see it like this, or you might see this, for example. Oh, sorry. So you might see this species, but this is still silver 1, or silver 1+. So let's put silver plus here. And that silver plus can be reduced to silver 0, which is a solid. And that's where you get a silver mirror on the test tube. So you might have seen this test done where you take your test tube and into it you put your solution which has an aldehyde in it, or something that you're checking to see if it has an aldehyde in it, and if it has an aldehyde in, then this happens. So we add an aldehyde and then we add our silver 1, and then we get a test tube which has got a silver mirror forms on the outside of it, and that is Ag0, it's a solid, and then we also have a solution of carboxylic acid. So 2 different tests, Fehling's and Tollens, and they both can be used to test whether or not there is an aldehyde present, but they test for the presence of an aldehyde. So if by another method you know that you have this carbon-oxygen double bond, so this this carbon-oxygen double bond, which is both present in both aldehydes and ketones, if you know you have this carbon-oxygen double bond, then you can use Fehling's or Tollens to tell you whether it's an aldehyde or a ketone, because they only tell you the presence of aldehydes. So if there's a different aldehyde in there as well, it'll pick that up. And they're also used, therefore, to detect whether a sugar has an aldehyde in it or not. So that's talking about oxidation and alcohol production we covered earlier. And we're now going to move on and talk about the final step of this lecture, which is elimination reactions. And this is where we can go from an alcohol and we can go back to an alkene. So I'll just so if I start, for example, with one of the ones we've been talking about, so if I start with propanol and I eliminate it, then I go back to propene. So let's look at that now. We're going to look at something called elimination reactions. And these are called elimination because they are eliminating water. Of water, we would say across a carbon-carbon bond. So if I have, for example, let's have propan 2-ol again, so I'll just use CH3, CH3, and actually let me draw out one of these because that'll help us. So if I draw out the one on the right, so if I have CH, H, if I add an acid catalyst again, then I am left with carbon, double bond to carbon, CH3 down here, CH here, H. So you can hopefully see from that that what I've done is I've lost this. So I've lost H2O, which obviously is water, so I've got H2O. And I'm left with the alkene product. So I'll draw this again skeletally because this is the way we prefer to do things. So there's my propan 2-ol. I'll just name everything as well. Propan 2-ol, also sometimes called isopropanol or IPA, isopropanol. And if I treat this with my acid catalyst, probably some heat, and I lose water, and I'm left with propene. You'll notice I haven't used a number in propene because there's only one option for it. You can't have anything other than propanene. So let's look at the mechanism for this. And it's fairly straightforward. So let's use our skeletal formula again, and we'll start down here. So I've got OH and I've got acid. And again, remember, free acid, free protons, free hydrogen ions tend not to exist. This will probably be on something else like, again, H3O+, but for simplicity, mechanistic simplicity, we can use the H+. So this oxygen here has a lone pair on it, and so the first thing that happens is you get this attack. So I've now got oxygen has more than 2 bonds to it. It's got 3 because it's got 2 hydrogens and 1 carbon bond, which means I give it a positive charge. And that now is what we call a very good leaving group. This is a good leaving group. We say LG. So this guy here is a good leaving group. And so that's what he does. He just disappears. Doesn't disappear. He leaves the molecule. So we draw is this bond breaking, and the electrons go to the charged species. So we're left with another charged species and water. Now, this charged species here has got a hydrogen hanging off here, and so if I'm in water, a different water molecule can come along now, and its lone pair can come and it can grab this bond, and then the bond between the hydrogen and the carbon gives its electrons back to the carbon-carbon bond. I'll just highlight it in red, so to this carbon-carbon bond. So I'll say that again. So the electrons in the bond between the hydrogen that I'm drawing in red now and the carbon that I'm drawing in red now, those electrons in that bond, so I'll just put them in green, there's 2 electrons in that bond, both of those electrons are given through the yellow arrow to the bond in red. So it's just a flow of electrons, and I'm left with this structure. So I've got a double carbon bond where I had a single carbon bond, and the hydrogen has been removed, so I've got OH2 with my additional hydrogen on it, and again that's now charged. So this is the mechanism, and you can probably get away with not using this part, so you can just show the hydrogen leaving and its electrons going into the double bond, but this is for completeness, this is what happens, so it's picked up by water, so you shouldn't be penalised for drawing that. So I'd encourage you to get used to drawing that if you can. Now you might have spotted here that we've done something actually that's quite cool, because if I start off with, for example, sugarcane, and I refine that, I get sucrose, which I can turn into glucose, which I can ferment into alcohol or ethanol, which I can fractionally distill. Let's use a different colour here, fractional distill, into just ethanol, or at least 95%. And then that I can do the reaction we've just done above, so I can add now acid catalyst, and now I have, in this case I would have ethene, and then if I take that ethene and I polymerize it, I would have polyethene, or sometimes just called polythene. I'll say polyethene. So you can see here what we've done is we have taken a natural material, sugarcane, and we have converted it into what we would consider to be an artificial plastic that we normally get from crude oil. So this is the power of the chemist. The terms artificial, or oh, it's got chemicals, I've made it from chemicals, or it's all natural ingredients, is all really a little bit of a misnomer. It's not really using the right terms when people say things like that, because something being natural, something coming from a natural source, doesn't necessarily make it fundamentally good. And something coming from crude oil, which is also a natural source anyway, doesn't necessarily make it fundamentally bad. The problem comes from when you do something in chemistry which is very difficult for nature to reverse, because then we have a substance in the natural world which can't find its way back to where it came from. And as soon as you start doing those kind of overall fundamentally irreversible reactions and those irreversible processes, you need to have a way of converting it back in a safe way, otherwise you end up with a build-up. And that's what's happening at the moment in the world with plastics. So because plastics, nature has no real way of breaking down things like polythene, it stays in the atmosphere pretty much forever. And we need to have a way of converting that back into natural processes. So for example, if you were to burn polythene, so let's add this in here, if you were to burn polythene in oxygen, you'll be left with carbon dioxide and water. And that carbon dioxide and water can then be used, make a bit of a mess of this now, to grow more sugarcane. So now I have a cycle. This is like the biofuel cycle. So again, it does not without its problems, but to get the plastic, to get the polythene from where it is, where it's locked all of that carbon up and all that energy up in a way that nature can't deal with it, to get that back into a natural process, i.e. the growing of a plant, we can achieve that, we can burn it. So all of these steps are things that chemists are perfectly capable of doing. So don't be fooled when people say, oh, it's come from a natural source, or it's got artificial chemicals in it. Chemistry allows us to move between these very straightforwardly. So this is everything on this topic now in terms of alcohols. So just remember this last step about elimination and the mechanism that you've got there, and along with that, the test we can do to determine whether we have what oxidation product we have an aldehyde or a ketone, and also how we go about oxidizing at primary, secondary alcohols, tertiary alcohols cannot be oxidized, and we initially spoke about how alcohols are made, which we touched back on there in terms of the fermentation of sugars. We also need to remember that they can be made industrially by the hydration of alkenes in the presence of an acid catalyst. So in the next lesson, we're going to talk about some analysis techniques. So these would be things that would inform you what sort of molecule you had. So if you had an unknown molecule in your test tube or in your round bottom flask and you were to find out what it was, there's a whole host of incredibly powerful techniques we can use to find those out. And that's what we'll cover in the next lecture.